Hello there. Let's talk about deletions in a binary search tree. Okay, so hopefully at this point you already understand binary search trees in all other aspects than just deleting. If you don't, see my other videos. In my other videos we talk about how to identify a binary search tree, all the rules that define it, some terminology. We talk about how to build a binary search tree with the insert or add operation. We talk about searching through a binary search tree and time complexities, and even drawing the diagram in a really nice and pretty way so that your trees are easier to debug. So for now, I'm just going to say it's time to learn how to delete nodes from a binary search tree. So there are three types of deletions. Actually, let me just kind of like, for example, suppose you want to delete the number 48 from the tree. Okay, well, first you'd have to go search for 48. So already you know this is going to be an O of H operation, or log time if the tree was perfectly balanced, or linear if the tree was really poorly balanced. So we're going to search for, what did I just say, 48? I should write it down. Let's say we're going to search for 48. We have to go search for it first. So that's going to be O of H. Once we find it, we then have to determine what type of node it is. How many children does it have? Is it a leaf with 0 children? Is it a node with 1 child? Or is it a node with 2 children? Each type of node is deleted in a different way. So let's see, the first type we would delete is a node with 0 children, also known as a leaf, also known as a external node. The second type of deletion is a node with 1 child. And the third type is going to be the hardest type. We'll do that at the end of the video. It's going to be a node with 2 children. Numbers 2 and 3 are going to be internal nodes, but I hope you already know that because you watched the videos. Anyway, so let's start off with the easiest possible node to delete first, just a regular leaf. So I'm going to delete this stuff real quick. And then just kind of like erase that and that and that. Okay, so let's identify a leaf. Well, it could be anything that just doesn't have any children of its own. Let's do the number 11 just to make things a little bit easier. So let's delete the number 11. I'll put 11 here. We first search for 11, so we look at the root node. 11 belongs on the left. We look down here. 11 belongs on the left. We look down here. 11 belongs on the right. We find 11. You know, if we reach the end of the tree and we couldn't find it, then it's like, I don't know, maybe throw an exception at the user. Hey, you tried to delete something that wasn't there. But the 11 is there, and now we have to figure out how to actually delete it. So let me draw a couple of larger representations of these nodes real fast. So I'm just going to draw like a big old circle here and maybe duplicate it. And we'll just pretend that that's the 9 and the 11. So I'll put like a tiny little 9 there because I don't want to change the font size, and a tiny little 11 there. And when we draw our diagrams, we usually just kind of do one line. But you should know that if you're doing this in code, actually what's happening is the 9 node, it's got a right child pointer that points down to the 11 node. And then the 11 node has a, let me just redo this real fast to make it prettier. And then the 11 node has a parent pointer that points up to the 9. This is probably going to be true for almost every language, at least that I can think of, that you would code a tree in. And then of course the 9 would have a parent pointer to, the 16, but we won't consider that. So what are you really going to do? Well, first you have to look at the 11 node and travel up to its parent and let the parent know that it no longer has a right child. So long story short, we're going to null the right child pointer. We're going to say disconnect that right child by setting it to null. Maybe I'll just put like a little null symbol here. Then we don't necessarily need to actually null the pointer on the 11 node because we can just delete the 11 node if we're using dynamic memory. If we're using a smart pointer, it should go away already at this point because it has no one else pointing to it. But long story short, once we kill the 11 node, we also end up killing its pointer. So we don't really need to tell its pointer to point to null. It's just going to end up going away. It's not going to be a memory leak because it was only pointing to the 9, and the 9 is not going to leak memory because the 9 is still going to be inside of the tree. So the time complexity, once we find the leaf, the node with 0 children, is just going to be constant time. We're just going to manipulate a couple of pointers, maybe call delete on that node. So it's really all about log time to go find the node if it was perfectly balanced, or just O of H to find it. And then plus constant is going to get canceled out. So it's like an O of H operation, or log time if the tree is perfect. So let me just cross it out to let you know that this is what it's going to be like. We're going to say the 11 is just gone, and so is the pointer that the 9 has pointing down to the 11. That's how you delete a node with 0 children. So deleted a leaf. All right, now the next thing, which is slightly harder, but not too hard, is deleting a node that has 1 child. Long story short for this, we're pretty much just going to, oh, I forgot to full screen the annotator. Let me do that to get myself a little more room. We're really just going to promote its 1 child to wherever that node was. So let me erase this real fast. And we'll say that, let's find a node with only 1 child. It's not the 35, it's the 32 node. Okay, I guess that's why I drew that. So let's kill the number 32. You know, if there was just like 1 child, like let's say the 23 was the only node that existed, and there were no nodes underneath the 23, then this would really be the same operation. We would literally just promote the 23 up to where the 32 was. But I wanted to do this example because it's a little bit more difficult. So we want to kill the 32. What we're going to do is first search for it. So this is already going to be an O of H operation, or log time if the tree is perfectly balanced. We go down here, we go down there. You know, where is the 32? We're just searching for it. So we had to spend the time to search for the node. We then look at the node. Okay, we found the 32. We identify how many children it has. We see that this is a node with only 1 child. And that means the 1 child, which in this case is 23, just needs to be promoted up to where the 32 is. So that means I'm going to just, you know, remove the 32 from the diagram, maybe get rid of one of these connecting lines, and then just move the 23 up a level. And that's pretty much it. If you're thinking about this in terms of code, you want to have, let's see, let me duplicate this again in a different way. If you're thinking about code, what you want to do is have the 32, which is the node you're going to delete, go to its child. So determine if it's the left child or the right child that exists. Once you find that child, you tell it that its new parent is the parent of the node you're trying to delete. So that means the parent of the 23 is no longer 32. The parent of the 23 is actually 35. You know, its original grandparent, or the parent of the node you're trying to delete. After you do that, you tell the grandparent that it's no longer pointing down to the node you're trying to delete, but instead to its grandchild. So again, we're just going to manipulate some pointers here. We're going to say, yep, your left child is now the 23 and not the 32. Notice how we're kind of, you know, drawing arrows around the original node. We're sort of cutting it out of the situation, just like in a linked list where you remove one node. And this is going to be a constant time operation, at least after we search and find the 32 node. Finally, of course, you want to like delete the 32. But so if this is like a regular pointer that you have in your tree, you would call delete on it, depending on your language. And then if it was a smart pointer, as soon as no other nodes are pointing to the 32, it's just going to go away. So you don't really have to worry about it. But yeah, long story short, notice how the 23 is actually the new left child of the 35. So that's why I say that the 1 child that was on the 32 is going to get promoted to wherever the 32 was, wherever the node you wanted to delete was. This will be the same whether or not, whether it's the left child or the right child, in terms of what is the 1 child that the node had. And also, you know, how do you decide how to tell the grandparent, is its left child pointer going to be changing, or is its right child pointer going to be changing? Well, you know, when you originally looked at that 32 and you were about to delete it, you could tell that it had that it had 1 child based on its left pointer and right pointer. One of them was null and one of them was not. So whichever one of them was null, that tells you the direction that the grandparent should be pointing. So in this case, the 32 had a left child pointer that was not null and a right child pointer that was null, because there was no right child. So that's why we told the grandparent that its left child pointer is now the 23. And that's it for deleting a node that has 1 child. Okay, so I'm going to go ahead and delete this, or sorry, I'm going to duplicate this one more time. And we're going to do a deletion of a node. Let me write down, deleted a node. One child. Yay, we did it, you guys. Okay, I'm going to put that there too, just for my notes. So this is going to be the hardest part. We're going to try to delete a node that has 2 children. Maybe I'm first going to delete the 35 node, since that's kind of where we're hanging out lately. And then we'll delete the hardest node of all, the 41 nodes. So the first thing we need to know before we can get ready for deletion is the in-order traversal sequence of the data in this tree. If you're watching this video as soon as I published it, then I don't have videos up yet on Traversal. I'm going to upload those soon. If you're watching this from the future, then you can just check out one of my Traversal videos. But long story short, in-order traversal just means produce a sorted list, an ascending list or a non-decreasing list based off the data that's inside of the tree. So, if I put this down here, I can just say, looking visually from left to right, this is why I draw my trees in this way. I see a 6, and then a 9, and then an 11, and then a 16, and then a 19, and then a 23, and then a 29, a 26, and then a 29, and then a 32, 35, 38, 41, 43, 48, 52, 59, 67, 73, and 79. Let me just double check that I've done this correctly. The numbers seem to be increasing, or at least not decreasing. Let me just double check. Okay, how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I already got lost. I think it's 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, did it right. So basically a sorted list, an ascending list of the original data that was inside of the tree. And now we need to look at a concept called in-order successor. Successor comes after, predecessor comes before. Think of like a king and a prince, right? The prince is the successor to the king. Eventually one day when the king grows very old and becomes grandpa king, and the prince grows up and becomes the regular king, then you would look at the prince king and you would say, who was your predecessor? Well, it's grandpa king, right? So whoever comes before is predecessor, whoever comes after is the successor. So we want the in-order successor of the node that we wish to delete. So I can't remember what I said originally, but let's just say we're going to delete the 35 node. I should have written it down. Let's delete the 35. First, we have to find the 35 itself to make sure it exists in the tree. So I'm going to look at the 41. I'm going to go left to the 16. I'm going to go right to the 35. There it is. We found it in O of H time in the worst case. So this is obviously not going to be the fastest operation, but all the ops are kind of the same speed in a perfectly balanced binary search tree. Not empirically, but in terms of time complexity. So we found the 35. We identified that it has 2 children. So then what we have to do is find the in-order successor. What is the in-order successor of the 35 node? It's, well, we just look at this sorted list, 35 here, and it appears to be 38. And that actually makes sense because since the data in the tree is going to look sorted if you sweep your eyes from left to right, assuming you drew the diagram well, you're really just looking for the node that is as close as possible to the node you wish to delete, but happens to be to the right of it. There are some tutorials out there that use the in-order predecessor, so that would mean the 32 would be the one you select, but let's not do that because I like to do successor. So first we find the 35, then we find its in-order successor. We'll do another delete maybe next of the 16 node because that'll be a little more difficult. Once we find the in-order successor, we're actually just going to copy the data up into the tree. So up into the node we want to delete. So that means I'm going to take this 35 and it no longer has 35 as its value. Instead, we're going to steal the value of its in-order successor. So 38 up here. So now we have 2 38s in the tree. That's bad. We need to recursively delete the 38 node. It's not really a recursive delete. It's more like you're inside the remove function or the delete function or whatever you chose to call it. It's usually remove. And after you've copied the value of the in-order successor to the node you actually wanted to delete, then you call delete or remove again on the in-order successor. You probably want to use a pointer to that node or have some sort of a way to reference that node without telling the tree to start deleting from the top again. Because if we just call tree.remove with the number 38, it's going to actually find the 38 on top. And that's going to be no good, because then if you've written your code correctly, at least after that point, then it's going to find the 38 and copy its value up, and then it's going to happen all over again. We're going to just be stuck in an infinite loop. So instead, you want to have like a pointer to this node or a reference to this node, and then call a removal function or a delete function that can receive just like, a reference or pointer directly to that node. And then if you notice, the number 38 node, the one on the bottom, it's a leaf. It does not have two children. So there's actually a guarantee that when you find the in-order successor, it will only have 0 or 1 children. It's absolutely impossible, unless your tree is super messed up in some way, that the node would have 2 children, because if it did, then you have not gone far enough to the left towards the node you're trying to delete. Remember we said we need to find the node that is as close as possible to the node that we want to delete, but just like on the right side. Well, if there's a left child, let's say the 38 had a left child, then we would actually want to follow the left child. We wouldn't stop at the 38 node. So it's impossible for the node to have 2 children, which means it's going to end up being an easy deletion. So the first thing we do is we're saying, let's delete a node with 2 children. That's the 35. We find its in-order successor, we copy its value up, and then we call delete again or remove again on this in-order successor, which is guaranteed to just be an easy leaf removal or a node with 1 child removal, where we just promote its child up, and that's it. So let me duplicate this real fast. And let me say also that everything we just did was basically it's just going to be O of H, because it's going to be O of H to go find the node in the worst case, and then O of H to find its in-order successor. Some fraction of each, O of H fraction, O of H fraction, but when you just combine them, it's just going to be O of H, or log time if it's a perfectly balanced tree. And then once we find the in-order successor and the node we wanted to delete, it's just a matter of just copying data and maybe doing the second delete. So, the second delete itself would just be like another O of H or log time. So you probably know at this point that if you have 2 times log of n, it's just going to cancel out to log of n if we're talking about big O time complexity. Anyway, so I'm going to duplicate this one more time and then revert everything to scratch here, or to the very beginning again. So we can delete something that's a little bit more difficult. Whoops, that's bad. Can I get this? Nope. Can I get that? Yes, okay. So let's delete that 16 node. So we can look at how you might find the in-order successor in a program, because you don't want to traverse the whole entire tree and produce a giant list and then scan the list and then find the successor, and then once you know the number, go search for the node. That's going to be way too slow. The tree should be way faster than that. So instead, this is kind of how you do it. Let's search for the 16 first. So we do 41, 16 belongs on the left side. We found the 16. Now we have to find the 16's in-order successor, the one that comes after. You can tell just by eyeballing it that it's going to be the number 19, right? But how do we find that number in the code to make it a little bit faster? So again, 16 and 19, they're just paired up right there. Well, first you just take a hop to the right. So you look at the right child, if it exists. If it doesn't, then you have not tried to delete a node with 2 children. It was definitely a node with the 1 child at most. So we take a hop to the right to find its right child, and then you follow left child pointers as far down as you can possibly go until you reach a dead end. So that means I'm taking a hop to the right, and then I'm just going to go, maybe I'll do another color here. I'll go left child pointer, left child pointer, the left child pointer, as far down as I can possibly go. And that is the successor. Notice how that's the 19. Again, if the 19 had a child on its left side, we would have to follow it down further, which means it's guaranteed that you will stop at a node that has no left child. If it had a right child, same situation, it's still going to be the in-order successor. But that just means when we call a remove a second time on that node, it's going to be a leaf that gets removed and not a node with one child. So it's just pretty easy. Let me say that now that we've found the in-order successor, we're just going to copy the value. So I'm going to do, maybe I'll put this in orange. So this 16 is no longer in that particular node. We're not even deleting that node. We're just stealing a value from a different node. We're going to steal the 19 value from the node, which is the in-order successor. And now that we've done that, we'll use our reference to the 19 node to call remove on it specifically. So when we call remove or delete, it's basically going to say, all right, what sort of node is this? It's not even going to have to search for the node because you gave a pointer to the node or a reference to the node. It's going to go, oh, this is a leaf node. That's easy. I just tell the 23 that it has no left child anymore. And then I just actually deallocate the 19 node. Or if it's a smart pointer, let it die on its own. Anyway, let's do something a little bit more difficult now. So I'm going to duplicate this and try to revert all this stuff. So I'm going to revert this. Okay. Let's delete the root node, the hardest node of all, the 41. Okay, so if we want to delete the 41 node, I'm just going to put 41 here so I don't forget. First we search for 41. In the worst case, it would have been O of H, but we were lucky, we just found it right away. Now we have to find the in-order successor for the 41. So again, take a hop to the right, and then follow left child pointers as far down as you can possibly go. So we'll look at the 48 here, and then we'll look at the 43. Now we've hit a dead end, and we know that the in-order successor for the 41 is 43, and that makes sense because they're paired up here in this sorted list at the bottom. So then the next thing that we do is we just copy the data. We steal the data from the 43, so I'm going to cross out this 41 here, and it's going to end up being 43 up at the top. And then we call delete a second time or remove a second time on the actual 43, which is another easy removal because it could not possibly have two children. It's only going to have 0 or 1 children. And well, that's pretty much it. It's just going to be just so fast and easy. So that means the 43 is gone when we're finished here. If you look at all the slides in this video, you'll notice that the data is still ordered correctly. So we do have a valid binary search tree, even after we kind of do this weird data stealing. Let me see if I can find something that would have had 1 child. So I want to look through the whole tree and see if I can find a node that has 1 child that would make a good in-order successor. And if I can't find one, I'm just going to manufacture one real fast. Let's see. Who has a right child only? No one has a right child only. That sucks. All right. Let's say we want to delete the root node again. And I think last time we just said it was the 43. How about we... that's boring. Let's delete the 59. Okay, so I'm going to write 59 up here so I don't forget. And then we're going to add another node real fast so that the 67 has a right child. Why am I doing this? Because the 67 is actually the in-order successor of the 59 node. So I'm just going to draw like another line real fast, like that. And I'm going to update some number. Let me just say 70 is going to be the number in that node. We just double check that it's increasing, 59, 67, 70. Okay, so we want to delete 59. The first thing we do is we go find the 59. So I'm going to take off my line tool. Okay, so we're going to go to the root. 59 belongs on the right side. So we find the 59. There it is. Now we're looking for the in-order successor. We go to the right side. And then we follow all left child pointers until we hit a dead end. Left child pointer, dead end already. Because, I mean, there is a right child, but we're supposed to be going down left child pointers. There is no left child pointer, so we've hit a dead end. So that means the 67 is the in-order successor of the 59, which means we're going to steal the 67 data and put it where the 59 data was. So again, we're not really deleting the node that had 2 children. We're going to eventually delete the node that had 1 child, the successor. But 67 is the number that's going to be there. And then we call delete on this 67. And what's going to end up happening is our removal function identifies that that 67 had 1 child. And so what it's really going to do is just promote the 1 child, which is the 70 node, just one level higher where the 67 was. So that means the 67 is just gone. We do actually delete that, and then the 70 node is going to be the new left child of the 73 node. Notice how the data still makes sense. Okay, I think that's all I've got for you. These are basically log time operations. Just one more time, log time if the tree is perfectly balanced. It's a little bit closer to linear time as the tree becomes more imbalanced. If this was a self-balancing tree, then this would be like log time in terms of worst case scenario. In general, we'll say that this is still on average. If we had just totally random data and totally random deletions, on average, this would be a log time operation. Even if we do log down to find the node and then another log to find the successor, that's still not going to be worse than log or O of H in general. Okay, that's all I've got for you. Thank you so much for watching this video. I hope you learned a little bit of stuff, and I hope you had a little bit of fun. I need to see if someone is selling pie at this hour. Going on a search engine. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video, and it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? Just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all. Hello there. Let's talk about